Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of what happens to a star following the end of its evolutionary sequence. And in particular, what we're concentrating on is what happens to the highest mass stars. And if you recall from the previous videos, that the high mass stars in our universe will suffer from a process called core collapse. And then the energy of the core collapse causes what we call a supernova. Well, the remnant of the material of the envelope goes off and expands into space. What's left behind is a very compact core that used to be the iron core of this high mass star. So let's go ahead and get right back into things. Now, the first picture that I have on the screen here is a way to help you sort of summarize and start to bring together the idea of what we're talking about here. So what we're talking about is the mass of the core that used to be this high mass star. So the remnant core that has, following the supernova blast or the supernova event, the core has collapsed due to the force of gravity. Now, in a previous video, what we talked about was for intermediate mass stars, when the core of the star is left behind following an event called a planetary nebula. The low mass stars don't do this, but the intermediate mass stars, the core of the star that's left behind, if you recall, was called a white dwarf. And if you remember, it was Chandrasekhar who was able to do the calculations to go with the physics of this. And what he determined is if the core is less than 1.4 times the mass of the sun, or 1.4 solar masses, then the electrons that are part of this core, due to electron degeneracy pressure, the electrons are able to hold up and suspend and keep this white dwarf a white dwarf, fighting off gravity for essentially all of eternity. Now, what he calculated was, though, is if the core that is the aftermath of the life of the star is greater than 1.4 solar masses, such as what a high mass star will do following a supernova, then it will become a neutron star. In the previous video, we talked about the details of those objects and how we find these objects. But if you remember at the end of the last video, Chandrasekhar also calculated that although neutrons have the very same ability to hold off gravity, they resist their ability to be crushed into smaller and more confined spaces, that if the core, if this neutron star is greater than 3 solar masses, then neutron degeneracy pressure is not enough to hold off gravity. So there's sort of a set of numbers that become critical. If the core is less than 1.4 solar masses, it's a white dwarf. If it's greater than 1.4 solar masses but less than 3, it becomes a neutron star. And then, of course, the question becomes, what if the core that survives the supernova is greater than 3 solar masses and gravity continues to crush and shrink that core down? Now, what happens is really all the consequences of gravity. If the remnant core is greater than the Chandrasekhar limit for neutron stars, then if it's greater than 3 solar masses, then what we have is essentially the idea that gravity is going to ultimately have its way with the star. So there is nothing that can stop gravity at this point. The neutron degeneracy pressure is not strong enough to fight gravity. There is a continual collapse of this core into something smaller and smaller and smaller. And the normal laws of physics are not behaving at this point, because normally when you shrink something down, the object has to become hotter as it shrinks smaller. But in this case, that's not going to happen. It produces no heat. Essentially, there is no force in nature that's going to stop the collapse of this remnant core. Now, when this happens, we have to invoke an idea that we talked about many, many lessons ago. Earlier on in the semester, we talked about a concept that was related to orbital mechanics, and the concept is called escape velocity. Let me remind you what the definition is. Escape velocity is the minimum velocity needed to escape the gravity of an object. So an example I gave weeks ago was that the Apollo astronauts in the late 1960s and early 1970s, when they wanted to leave the Earth and go to the moon, to land on the moon, they had to be able to escape the Earth's gravity. So there was a minimum speed necessary to go fast enough so that the Earth's gravity doesn't pull you back and doesn't make you come home. So it's literally as it sounds, the escape velocity. Now this is the formula that we saw. The escape velocity is equal to the square root of 2gm over r. G is the universal gravitational constant. M is the mass of the object you're trying to escape. And r is the size of the object that you're trying to escape. Now here's the critical part I want you to pay careful attention to. Notice that the r, or the radius of the object you're trying to escape, is inversely proportional to the escape velocity. Now what that means is even if we ignore the square root, 2 is a constant, g is a constant, m isn't going to change, what you'll notice is as r changes, v has to change as well. And because they're inversely related, what that means is as r gets bigger, v becomes smaller. What that means is if the object didn't change its mass, but changed its radius by getting bigger in size, then it would be easier to escape. However, if r gets small, then v becomes large. So if an object doesn't change its mass, but it shrinks smaller and smaller and smaller, then what happens is the escape velocity becomes greater and greater. So essentially, I've got a little animation here to kind of visually show you the point. If this object shrinks smaller in size, then the force of gravity associated with the object becomes larger. So an object's gravity is related to its mass and its size. If you continually shrink the object smaller, the force of gravity associated with the object becomes bigger and bigger. Now the reason why this is relevant is because what we're talking about is the core of a star that has shrunk due to gravity following the supernova. And so what happens is if this core is greater than 3 solar masses and it shrinks because of gravity, it will not stay a white dwarf, it will not stay a neutron star. There's nothing to fight gravity. It will shrink and shrink and shrink. Now the idea is if the object becomes small enough, the v becomes big enough, remember they're inverse, that you can make r small enough to make v bigger than the speed of light. So if an object shrinks smaller and its gravity becomes more powerful, there comes a point when to escape the object would require you to travel faster than the speed of light. And if you remember from a previous lecture, that there is no traveling faster than the speed of light. It is the fastest speed that the universe allows. So what happens is the object turns into a black hole. So not even light traveling at the speed of light can escape this object because you have to travel faster than the speed of light. Now, black holes are often misunderstood, and I'm going to just spend a little bit of time telling you a few things about black holes. Let me start off with the first part. The name black hole is actually a misnomer. In other words, it's not technically correct. Let me tell you why. First of all, black holes are not black. The idea of the word black in this case related to science, remember black is the absence of all color. White is the presence of all color. Black is the absence of all color. But a black hole isn't just black because it's the absence of all color. A black hole is the absence of all electromagnetic radiation, all forms of light. Because remember, all forms of light travel at the same speed. So if, let's just say, the color red can't escape, well, neither can gamma rays or neither can radio waves because they all travel at the same speed. So a black hole does not allow any light at all, any form of electromagnetic radiation to escape. So the word black is, well, quite frankly, not black enough. In other words, a black hole isn't just the absence of color, it's the absence of all light totally that could possibly be produced in our universe. The other thing is, a black hole is not a hole. And here is a picture that you often will see where people will show you this construct to give you an idea of a black hole, but what they don't tell you, unfortunately, is this is what is typically just a map, a three-dimensional map in two-dimensional space to give you the concept of a black hole. So a black hole is not literally a drain like this shows. It almost looks like a drain in your bathtub. A black hole is an actual object. It's a thing, but it does not allow anything to escape it. So it has the behavior of a hole. Think of it as a hole that you could put something in, but you just can't take anything out. So unfortunately, this representation is not really what a black hole would look like, but it is a mathematical description of the behavior of a black hole. So they're not black and they're not really holes. Well, so what are they? So let's put this all together now. So any object that's the remnant core of a high mass star, if it's greater than 3 solar masses, that thing becomes a black hole. Now here's the problem. If you can't see a black hole, in other words, how do I portray it in some sort of an illustration? So a black hole is something that is shrunk very, very small. So let's pretend at the tip of this arrow is where the black hole would be. We actually give it a name. It's called a singularity. By definition, a singularity is something that occupies a point in space, but it has no actual size. So a singularity is the description of a black hole, and its radius will be 0. Gravity has shrunk it down to a size effectively of 0, no measurable size, but yet it still retains the mass of the object that became the black hole. Now, in physics, when you have the mass of something have a size of 0, that makes the density become infinite. So a black hole has no measurable size, it has its original mass, and it has an infinite density, which is kind of bizarre all by itself. Now, when it comes to describing black holes, here is often what is quoted or described, but not fully, and so leads to some confusion. So let me try to clarify a few things here. The black hole itself, the singularity, has no size, it has mass, and it has an infinite force of gravity associated with it. So let's pretend this dot is the singularity. Now, where the singularity is, the escape velocity is infinite. This is the symbol for infinity. So if you wanted to escape this point, you could never do it because you can never travel infinitely fast. But one of the things we know about gravity is that it gets weaker with distance. So if I get further away from the singularity, let's say I never get any closer than right here, well, the escape velocity is no longer infinite because gravity gets weaker with distance. But at this point, the escape velocity is still greater than the speed of light. And since nothing travels faster than the speed of light, I still can't escape. So even staying at this comfortable distance right here, I'm still not able to escape this black hole. But let's say I don't even get that close. Let's say I never get any closer than this distance. Well, at this distance, the escape velocity has become lower. It is now equal to the speed of light. Well, what that means is if you could travel at the speed of light and you never got any closer than this, you could theoretically go home. The problem is you cannot travel at the speed of light, so don't even get this close to it. Let's say I never get any closer than this distance way out here. Well, way out here, the escape velocity is less than the speed of light, which means if you were to show up with your spaceship and never get any closer than this, assuming you had very powerful rocket engines, you could escape and go home. Now, what I want you to notice is this now provides a boundary that is if you get closer than this boundary, you never go home, you become part of it, or a boundary where if you stay above this distance, you could theoretically go home. So this boundary between never leaving and the possibility of leaving is called the event horizon. The reason why it is called the event horizon is because anything that were to happen, any event that were to happen inside of this zone, you will never know about because all information can't travel faster than the speed of light. So any information from inside of this region, the universe will never know about because it can't ever escape. Now, even though on this picture I've shown it flat as if it's a disk, in reality it's in all directions. On all directions, this event horizon happens to be surrounding this black hole singularity. So we can describe the size of a black hole based on the size of its event horizon. And as long as you don't get closer than the size of the event horizon, you can observe the black hole and go home to tell people about it. But if you were to get closer than that, then you're not going home. Now, in the next video, we're going to wrap up the concept of black holes, and I'm going to show you some interesting things about the event horizon, and then, of course, explain to you how do we discover an object that does not reflect or produce any sort of light at all. How do we find something like that? But stay tuned to the next video, and you'll find out as well. I hope you'll join me.